I wanted to begin this talk by a short story about a man who was actually heading home with a donkey. He had spent a whole long day, doing some shopping and whatnot, and he loaded the donkey, on his way home. And then it was getting late at night, and then he decided that if he followed the usual route that he followed, he may not make it. So he decided to take a shortcut. Okay. And then on his way, the donkey actually falls into a big hole. And then the man starts climbing around, wondering what he's going to do. But eventually he figures out he had a spade and a shovel. So he decided he's going to dig, remove all the soil, so that he can actually get the donkey out. At this time, the donkey is complaining that, well, my God, how did you let me down? And then eventually he gives up after a couple of hours. Then he decides, you know what? I love this donkey so much. After all, it's Valentine, isn't it? So I love this donkey so much. So what I'm going to do is that I'm going to try to bury this donkey, so that, because I don't want to see it suffering, so the best thing is to just bury the donkey and forget about it. After all, I don't want to endanger my life. So the guy started working on this thing, shovel after shovel, throwing the soil into this hole. And then eventually, as he was getting tired, then he looks around and saw a big animal standing behind him. Then he wondered, oh my God, are the lions here to eat me or what? And then so he started running as fast as he could. And then in the process, the big animal is the donkey. So the donkey sees the farmer and he says, oh my goodness, this guy is now leaving me. So he goes after the guy. And because it was injured, because it fell into this hole, so it could not catch up with the guy. So the man goes there, hammering, goes to the house, bolts the house, making sure that the animal that was following him is not going to get him. So anyway, to cut a long story short, so he wakes up in the morning. Now the first thing that he sees is the donkey looking at him. And then the donkey is actually wondering, my goodness, why did you leave me yesterday? So the moral of this story is that it has three lessons. The first one, shortcuts are not always shortcut. They may end up being a long cut. So that's the first message. Now, the second message that I wanted to pass to you is that sometimes bold things sometimes can lead to greater things. Now remember, this guy just decided that even though the donkey, huge as it was, had fallen into this hole, he decided that he's going to try to get it out. But unfortunately, he was not able to do it. So what does he do? He starts, throwing the soil. So through that bold thing, he did something that he was probably not planning to do. But in the process, and this is the main message, the inspiration message, the donkey itself refused to quit. Every spade of soil that was thrown into this hole, the donkey would just shake off the soil and keep moving up. And every spade that came, the donkey just shook the soil and came back up. At the end of the day, the donkey was saved. So today, there is no one who can speak about this subject better than Peter is. So let's give him a round of applause for coming up here. He has been through a lot, for sure, no doubt about it, in his life. And he also has done great things in life. And we are going to hear all those stories, how he's managed all the way to come to where we are. So please, help me welcome our speaker, Peter Hildebrand.
How can I follow that? Oh my. And I don't know anything about donkeys either. So Bill warned me that this was really a difficult job to put something like this together. And he's really right. Because you go back and you're searching for this and for that and the other and trying to have all of your memories and stories intact and figure out how can I go through this and explain all of this to everybody. The title. This has to do with, the first two lines have to do with my grandfather, so we'll start out there. And DOGS is the Department of Geophysical Sciences at the University of Chicago. They called them, DOGS was what they used, the name. And you know what NCAR and NASA are. So I'll just go through a brief history of what I did in order to get here. And another week or two would have been a real advantage in making this better talk, but it is what it is, and we are where we are. A lot of my origins really center around a couple of people who were the mentors and people who guided my life, and really the strongest is from my grandfather here, a man with a big smile and an ego to match. And he's a person who was not constrained by a whole lot of things. He was a physical chemist. He went to the University of Pennsylvania, and he grew up scientifically in an age in which when he went to do his postdoc in Berlin with Nernst and a few other people whose names you may recognize, people like that. The senior professor's opinion was the law, and so he was at a time of transition, and that wasn't exactly the way he liked to think about things. He came back from his postdoc to a faculty position, and then very quickly decided he wanted to go to California, and in 1907 went to help start the Department of Chemistry at Berkeley.
Just going to ask that question because I got my PhD at UC Berkeley. We had a Hildebrand Hall over there.
That's named after my grandfather, yes. Right, and he taught Chem 1A. He probably single-handedly taught more students than almost anybody. I'm sure there's a few, but he proudly taught that and taught lots and lots of students. And there was no shortage of advice from Grandpa about how to live your life. Just none at all. But he also led us to do all sorts of enjoyable things. There's pictures of doing things like sitting on the edge of Half Dome. How close to the edge are you willing to sit? You didn't do that with Grandpa around, but that's the sort of thing he got us, all of his grandchildren, doing. Climbing mountains here with a bunch of family members. Another mountain picture. A lot of going to the out of doors. His area of research was in solubility. And so as a kid, of just 7 or 8, he would come to visit. He would fly from California to Chicago, where I lived, and then kind of descend on me with pictures, graphs from his papers, and start explaining this stuff about the solubility of chemicals. And it was a little hard for me to put it all together, but I got to listen. And that was what I was going to do, and he forced me to learn how to take square roots longhand. That never benefited me in any way that I could figure out. And it is a rather tough, obscure process, but actually you can do that. The things that he did leave with me, a number of things. One is he was really good at getting the family together. Here you see a family picture of Grandpa and Grandma and all of their offspring and the offspring's spouses and all the grandchildren, with him sitting proudly in the center of all of this. And so he was very proud of having this family. He had 4 kids, and they all got married and had kids and the like. And he would drag us all together in California to do things like this. And also on those trips, there was a lot of teaching that went on. And these were sort of the basic rules of going to the mountains with a group of people. Usually family, but maybe not. He was also the president of the Sierra Club, which was probably the first national conservation organization. And that was right after the Second World War. And so these things just got hammered into me as a kid. First of all, have fun with each other and with the experience. Know where you're going and how you're going to get there. Now that's it sounds stupid to say it, but you'll find a lot of people lost in the mountains who don't know where they're going, much less how to get back. Another thing that they just hammer into you, let somebody know where you're going, where at least you think you're going, and when you should be back, and tell them when they should start getting worried if you don't show up. And make sure people eat and rest. And another very important thing is keep the group together. They stay together. You don't let stragglers fall behind. You don't let people go way off ahead. You allow some amount of, wandering, but there's got to be some control. And then there were some leadership lessons that, I learned these early on, and this is part of who I am as a leader. It's part personality, and it's part of things that I learned here and then later in the Navy. But one of them, and then in the fire department, when I was on the fire department, is that the leader, the way I do things, the leader needs to be in the front when you're making decisions and working with people to do that, making sure people know where you're going and what you're going to try to do. And then you basically have to be at the back so you can watch what's going on. You can't both lead the party and be in front of it at the same time, except in some cases. So that was pretty much, I heard that more than once. And the other one, of course, is have a backup plan for everything that can go wrong, and have a backup plan for when that goes haywire, because it will. And these were just life lessons that I heard over and over again. And so we went to the mountains and we had fun, and it was a great childhood. We would drive back. I'd go back up there. We would drive from Chicago, where I lived, and back to California and do some mountain trip that Grandpa had planned for us. And we'd go up to some place in the Sierras and camp for a couple of weeks and wander all over with different parties going off in different directions. But you told somebody where you're going and when you were going to get back and the like. And we had. Which one is you, Peter? Which one is me? I am that one right there. You got it. Anyway, when I was about 6, my father, my father finished his PhD, and he went to the University of Chicago. So I went to Chicago too. He'd been a chemistry student, and World War II came along, and he was a junior at the time. And Edward Lawrence walked up to him one day, because he'd been doing things in the radiation lab in Berkeley, working there, and they'd all sort of kind of stopped taking courses and were doing supportive things in the lab. And one day Lawrence walked up to him and said, "Roger, you're going to Oak Ridge. You have to decide by the end of the week whether you're going to go in the Army or you're going to go as a civilian." So that's how I was born in Oak Ridge, Tennessee, because my father and mother went to Oak Ridge, because you kind of did what Ernest Lawrence said. Anyway, so he came back, got his degree, and at the time he came back and he switched into physics, and at the time they were building the first cyclotrons, and there was a cyclotron at Berkeley, and there was one at Columbia, and Chicago was building one. And my father, being at that point, a grad student, had the job of getting the beam out of the cyclotron. The cyclotron is this thing here. Here is a picture of the core of the Chicago cyclotron, not a very good one, with somebody sitting on a chair between some of the magnets, just to show you the size of the thing. And basically you have these two parts of the magnet, and you inject some particles, and you cycle the magnets, and you get the particles going around. You have a whole bunch of magnetic fields in there, and you get it going around really fast, and then you have to do some magic with other little magnets to get a beam out of it, so that you've got this beam of particles coming out. And my father is the guy who was able to figure out how to get the beam out of the Berkeley cyclotron. And so he was asked to come to, when he was still a grad student, to come to Chicago and get the beam out, because they built the thing, this one, and they couldn't get the beam out of it. And so he went and did it. And in talking to him, he says he doesn't really know how he did it in either case. It it was fiddling with little magnets and things like that, and you had an idea of what should happen, but this was just fiddling around until you got it to work. But on the basis of that, they hired him. And so I went to Chicago. This is the control room for the magnet. That's Fermi. I remember the control room. I don't remember Fermi. I remember a lot of the other notable physicists who were at Chicago then. It was quite a crew. I mean, you just see the list of them all. And I had the privilege of going and helping. My father let me come with him. And what he was doing was using the cyclotron to get this beam of particles out, and then using a bubble chamber. Here's a picture of him holding a bubble chamber. At that time, this was just a very, very little device. Basically, it was a flask with liquid helium in it, and you would cycle the pressure on it, and so that you would drop the pressure so it was about to boil, and the particle would go through, and you'd take a picture of it. So you drop the pressure and take a picture and hope you got something. And just do this over and over and over and over again. And then you have cameras looking at this little thing from 3 different points of view, so you could really resolve where the particle was going. And this is just a picture of a bubble track taken from one of these cameras. And so you'd go into the, as a kid, I don't remember how old I was there, but probably not 10, going in there, and in this huge room, they had the world's largest high bay, as far as I could tell. And it was just enormous, bigger than anything that I've ever seen in earth sciences. It was a whole building that was this high bay with a big crane on top. And it was that big because this is a big, heavy, solid piece of steel that was bolted together. And then it was surrounded by a whole bunch of pieces of concrete. And to get in and out, you had to go through a door, and there was a door that was this huge piece of concrete that would rumble closed or rumble open, and you had to go down this passageway that was about as far across as this room. And I'll tell you, that passageway really scared this little kid when I was little. But I got to go in and see this thing. It was quite something to see that and to see the other people. And I didn't have really that much of a appreciation of, the amazing group of people that was there. I would just hear my father sort of reverentially speaking of some of these folks. Fermi, and later Chandrasekhar and Yang and Lee, and a list of Nobel laureates that just went on and on and on. It was just sort of amazing to be around them, but I'd had relatively little connection with them as see them, they'd come over to the house sometimes for dinner or something like that. So I grew up in Chicago on the campus, and these are just a bunch of pictures of Chicago. Lots of snow here. Lake Michigan used to freeze every single winter, and we'd walk out on it as kids, walk out on the frozen ice, and there'd usually be 4 or 5 of us little boys who had not told our mother where we were going, and playing around on the ice, and usually not falling into the water, but sometimes falling in. And that was and a lot of fun just in the park in Chicago, riding our bicycles all over the place. And my friends and I were basically let loose in the city by our mothers to do whatever we wanted to do. And the rule being be home by 5. And we got ourselves into all sorts of trouble and got out, but it was a lot of fun. Of course, living around the university, playing in on the campus, going sailing on the lake a few times, not that many, but enough to really enjoy doing it. And just growing up and enjoying a big city. And enjoying the diversity of people in the city. And that's one of the reasons I like DC, is it's very much like Chicago in that regard, is it's a city, it's kind of small compared to Chicago, but the same sort of diversity of people and the like. And it's just always been nice for me to be able to continue living with a really diverse population and the like. And so, you know, I grew up, went to high school, eventually transferred into the University of Chicago High School, and then when it came time for college, I only applied one place. You know, these were different days, and so I went across the street to the university. And I can't say as during the first couple of years I was really that engaged student. The gen ed courses really didn't do a lot for me, most of them. I liked the science and math courses, Soc 1 and Soc 2 and humanities. And it's like, they were interesting, but you know, I wasn't really excited about them too much. But there was another life I had during this whole time, and that was track. This is another mentor of mine. He hated that picture. That's Ted Hayden. He'd gone to the university and had been a social sciences, in social sciences department, got a master's and was working for various folks in Chicago, and there was some very interesting community development stuff he was involved in there. And eventually became the track coach. He'd been a field, done field events, shot put, discus, throwing the hammer and things like that. And I don't know how, I really never did figure out how he became a track coach, but he ended up being the Olympic track coach in 2 different Olympics. After I was, after I finished with the university, but was still running as a graduate student on the University of Chicago Track Club. That's what UCTC is, University of Chicago Track Club, which had a lot of Olympians on it. And so we ran in the park, and we had fun, and ran in the field house. And one of the things I learned there is I learned a lot about how we all have different gifts. With the same amount of working out, I could pretty easily beat everybody on the team, and almost everybody on any team we ran against in the small college conferences. And I was doing exactly the same workouts. I was just a better runner than they were. And so, you know, I went and I set all the school records from a half mile up, and, you know, won all these races and things like that, ran lots of things. And Coach was the sort of guy who would just nail you with whatever, you know, whatever was going on in your head that was maybe a little misguided. I mean, he was the sort of guy who, I distinctly remember, you know, one of the African-American friends of mine on the track club saying, he was trying to remember some other black guy, and Coach was the kind of guy who could say, "What's wrong? They look all the same to you?" He could do that, and he would skewer you for whatever, you know, for whatever he noticed. We all just loved him. He was just a great guy. Edward M. Hayden. We all called him Meathead behind his back. That's what, he was smarter than any of us, I think. But this is his a little bit of his excuse list here, which you may or may not read. It was a real mark of creativity to get a new excuse onto his list, because he'd heard it all. But you know, with Ted is what we called him politely. With Ted's leadership, you know, lots of people just ran so much better and excelled at use their capabilities to the best of their ability or beyond a little bit, because Ted could lead you to do that. And he also could do things like, when I got too cocky, he'd get me into a race that really showed me how good I wasn't. You know, and so, you know, running for Ted, you know, I've lost to the best in the world in many races. Like Jim Ryan, some of you may remember his name as a distance runner. Well, I've lost to Jim Ryan and Rick Wohlhutter and Lowell Paul and a lot of other really, really good distance runners. You know, sometimes not even in the race. You know, the race would start and you run along, and then you get to the last lap, and a new race would start that I wasn't in. You know, but so I had these two aspects of being at Chicago. One was track, which was sort of a social club and thing, and the other was academics. In the first 2 years, I was just sort of plodding through the requirements. But then in the third year, I got into the Department of Geophysics, which was just an amazing place to be. There's a list of just a few people there. Rossby, Eric Paulman was a visitor there, Sverre Pedersen, Dave Fultz. When I first got there, Dave Fultz had his fluids lab here, and what he had is was doing these rotating tank experiments. And this was at the time before they'd figured out how to do numerical weather prediction modeling. And so what he had is these tanks that were about this big around, and you'd heat it at the center and cool it at the exterior, and you rotate it at some speed, and you'd look at, and you'd put a disturbance, a little hill in there or something or other. And this whole device, there's a camera up here and a bunch of lights, and the whole thing is rotating, so that the camera was rotating with the tank. And then you could watch the long waves develop and dissipate and turn into eddies like this. So you hear wave. This is just a progression of different waves as in the tank. And I would have really liked, when I was a junior, this is when I moved into the Department of Geophysics, and sort of education really clicked for me then. It's, this is what I ought to be doing. He wasn't taking undergraduate students, so. But I got to know about it, and I did get a job with a guy who was doing measuring waves. He had a wave tank, and this is just a bunch of devices he had in waves coming on shore. A little picture of an acoustic velocimeter that he used in the water. And so I worked for this guy for quite a while, and then he lost his funding, and I was sort of summarily moved by the department. It's interesting that the department would just take an undergraduate research assistant and just plop me into another lab. And so I was plopped into Roscoe Bram's cloud physics lab. And they were doing a project called Project White Top. And this was the first really carefully randomized cloud weather modification experiment that was ever done. Before, there'd been a lot of work with a guy named Henderson and a few other folks who would go out and burn silver iodide or some other chemical in the presence of clouds and claim to make rain and sell their services to agricultural districts or to the ski areas or whatever. And most of this weather modification that was being done was just being done on the basis of allegation. Oh, I'm doing this, and this was, it's patent medicine. This experiment was the first one where they were doing a very careful experiment. They looked for days that met the criteria for what they thought were modifiable cumulus clouds. And then on a random basis, that they would fly the airplane that would put the seeding material out. And only the scientist in the back of the airplane knew whether they were actually putting seeding material out or not. I mean, it was very carefully controlled. And then they looked at the structure of the clouds on a TPS-10 weather radar, which was a air surveillance radar from World War II that had been modified. And it would basically, it was looked up and down like this and scanned up and down and around slowly, and you would get these pictures that look like this. This is the data from the experiment. And what I was hired to do, this is a real good student job, is to use a grid, sit in a dark room with a 16 millimeter projector, put a frame up on the thing, and then measure the shape, the size, the height, and the width of these radar echoes from these clouds. And This was an immensely boring task, I have to tell you. But, that's what you have students for, is to do things like that. And they told me fairly early on that don't bother to try to figure out which ones are seeded days and not seeded days, because we've been working at this for several years and nobody can figure it out. That's all it took. After a month of it, I went and announced I could tell. And so then they didn't believe me, so they gave me a test, and I passed. I think they gave me like 20 days, and I got 18 of them correct, whether they were seeded or not seeded. And that was my first paper, actually. To write that up and submit it as an undergraduate research paper. And as I look back on it, it's kind of a disappointing paper. But then I was an undergraduate and didn't know much about any of this. But my hypothesis was right. And I figured, well, if the seeding works at all, it's going to make the clouds be taller. So I was looking for taller, narrower clouds. And I pretty soon learned how to figure it out. So I did that, and that was my first initiation to weather modification. After I went to the American Meteorological Society conference and to collect the award, I guess I was a junior. That must have been in the winter of my senior year as an undergraduate, to collect the award. And a guy named Pierre Saint-Amand, I don't know if anybody's ever here has heard his name. He was the head of the weather modification group at the Navy Weapons Lab in China Lake. And he was there. And he came and invited me to come to China Lake for the summer, which I did. And I'm wondering which year that really was, but I think that's the correct year. At any rate, so I went, and so that summer I went to work at China Lake, and I saw some of the true charlatans of weather modification. What Pierre was trying to do, when I don't think he was a charlatan, but he was doing anything had been asked by the Navy to do whatever he could figure out to do to figure out how to make it rain more over the Ho Chi Minh Trail, because Vietnam was roaring along at that point, and they wanted the trail to be slippery. And so he was working on warm rain process weather modification. So that they had a field site up in Northern California where they had a lot of fog, and they had people coming in with all sorts of secret weather modification ingredients. And I actually got sent up there by the base commander to take a look, because the base commander didn't believe anything realistic was going on up at this weather site. And I went up there and looked and came back and told the guy, no, nothing useful is going on up there. It's just smoke and mirrors. And he said, he thanked me for everything he did, and then he said, okay, now I want you to get any notes you took, go out behind the house and burn them. That was the end of that. Anyway, I don't know what happened. I had that summer, and then I came back after that summer to the cloud physics lab, and for that academic year, and that was the year during which I was going to, at the end of the year, I was going to get married, and then I was going to go in the Navy because Vietnam was roaring along, and my draft board had made it clear to me that either I could go into the service of my choice or I could go into the service of their choice, which I didn't want to do because I didn't feel like carrying a gun in Vietnam and shooting at people and being shot at. So I went into the Navy. But before I did that, I took my first research airplane flight, and that's where my sailing knowledge came in to save me, because we got into this Lockheed Lodestar, which nearly killed your brother too. Well, this is where I nearly died. And this is the one flight I went on in this airplane. The airplane gets down to the end of the runway, and this is Bemidji, Arizona, which is a non-controlled airport. And just in everything's okay, put the power on, start going to takeoff roll, and just as that was happening, the Northwest Airlines airplane came in over the trees and started landing on a cross runway, and with both of the pilots, of course, looking straight ahead, not looking off over there. And I happened to be sitting in a seat behind the co-pilot, and I was looking at the pilot, and I could see in a little window this airplane coming. And it was just stayed there in the window growing bigger, and I'd done enough sailing to know that constant bearing and decreasing range means collision. So I tapped the pilot in the shoulder and pointed him at it, and we actually had to go off the runway to avoid the other airplane. So that was, at that point, I went into the Navy, and I had a perfect record. I never once got on one of these things. Instead, I was at, while I'd been at China Lake, this is the lesson here is you need to get to know people and to tell them about your life, because I let people know that I was going to probably go into the Navy because I'd gone around and shopped the services, and it was the best deal. Aside from being the most intellectual of the services, so the most interesting from that point of view. And one thing led to another, and my good friend Pierre Saint-Amand recommended to me there was a base inspection going on at China Lake, and he had the captain who was doing the base inspection and come and talk to me about this, and the guy said, well, do you really want to go into the Navy? And I said, absolutely. And he said, all right, well, I'll fix it up, and you can go down to LA next week and get your physical, and it will be arranged that you will go to Monterey, California, Fleet Numerical Weather Central. And you've got to trust me. Nobody will ever confirm this until you get your orders, but they will come through. Well, you know, I had to accept the option that was in front of me, and I did. And I spent 3 years at Fleet Numerical, where I learned to program. I can't say as I had a great time there, but I learned a lot. I learned how to program and wrote programs to do verification of the forecast model and to do data ingest, quality control, and did some work on their terrain model. So I learned a good bit about what you do to do weather forecasting in the about 1970 era. This was 69 to 72. I learned a lot. I came back with a lot of skills in computing, and did not go back to the cloud physics lab because I decided that if I stayed in that lab, I might never finish because nothing much was happening there. It was just going very, very slowly. And I see two other fellow University of Chicago folks there grinning about this. And so I went into Dave Atlas and Ramesh Srivastava's lab, and that was really amazing what was going on there. There were at that time 2 Doppler radars, weather radars, in the whole world. One was operated by Dave Atlas with support from Illinois Institute of Technology and the Illinois State Water Survey. And so I was part of that. And the other one was operated by the National Center for Atmospheric Research, NCAR. And they couldn't really get it going, the NCAR one. And we had a signal processor that could process, I think, 32 range gates, and then it would dump out these Doppler spectra. And so data processing was a mess. But we learned to, and we take this thing down to Norman, Oklahoma for spring field experiments. And this was about the time, this is in the early to mid 70s, when hook echoes were really discovered. And so, I had experiences such as being at the radar, identifying a hook echo, and then in the communication with other radars, because by the time we got very far down this road, Norman had some, I don't know if they had a Doppler radar. I don't think they had a Doppler radar, but they had another couple other radars. Identifying this and calling up to the sort of the experiment control and saying we have a hook echo, and then having them say, well, phone it in to the Weather Bureau. And well, who do I phone it to? Here's the number, phone it. And I was pretty nervous to do that. Phoning in, this is hook echo observed at some location, and then, within a few minutes, having it come back over the Weather Service broadcast, which we were playing, and having a tornado occur that day as a result of it. And it was just amazing to be part of this. And I'm sure this wasn't the first hook echo observation that made it into a forecast, but it was, early on. It was just, incredible to sort of be there for that, and it was both frightening and thrilling to put that warning out there when it hadn't been done before. And this is just a picture. This is actually a picture of that radar, but later on when we had a X-band radar next to it. And this picture actually was taken when we were running the radar, which is now called the chill radar, and is at the university at Colorado State University, and they've upgraded it significantly now. That was just a picture taken inside the radome. There was a multi-year weather mod experiment that was trying to inject nuclei into the updrafts of hail-producing thunderstorms. The idea was you put enough nuclei in, you have competitive growth of all these little particles, and so you wouldn't get the big hailstones up like this. That big, 8 inches, is the world record, if I remember right. I used to have a casting of the world record hailstone that Nancy Knight made for me until somebody decided they needed it more than I did. And it went away. At any rate, there was this hail experiment because the Russians had been using howitzers to shoot seeding materials into thunderstorms in Russia, and they claimed a whole bunch of results. And so that the US weather community said, well, we're going to do it too. And they went up and they tried to modify hailstorms, and it was a tremendous non-success. It turned out that the Russians didn't get any success either. They just alleged they had success. So that sent the United States off to try to do the same thing. So that was my second big weather mod experience. Not something I would want to continue. But it was really interesting to come from this lab and then go to NCAR and get involved in all sorts of field projects. And we've talked about radars. I'll just show this last radar picture here. Well, there's the CP2 radar. Next, I think, I don't remember what that radar is. This is CP2. We're all familiar with color displays of weather radar data. Well, they were invented at in the Atmospheric Technology Division, NCAR, shortly before I got there. And it would have been in around 1980 or something like that. So that's just how you do it. These are just little patches from 2 field experiments that I had the pleasure of going on, and Piers is very familiar with one of these. That's where I first met Piers, and it was prior to going off to do HAPEX. Yeah.
Digging holes in the ground.
Yeah. And I put these up here because they bring back such memories. NCAR had a very rational point of view about going on field experiments. And so what these were great science experiments and a huge amount of fun, because there were no restrictions on taking additional time for vacation or making your own reservations or anything like that. So on this one here, I realized, oh, this is an opportunity to go take my whole family to Toulouse, France for the summer. So we did. We went over. I went over. I was working with the NCAR King Air aircraft here, and I went over and set things up. And when school was about to get back, I flew back, got the family. We returned to Europe. Spent about a week decompressing on the coast of Brava, and then went up to Toulouse where we just had a fantastic time going off and flying. This is not Toulouse countryside or the Pyrenees or anything like that. That's Colorado. But we were flying around over the Gironde and the Aude River drainages to the south and west of Toulouse, looking at the effects of terrain on the boundary layer and trying to do a whole modeling of the water balance there. And so there are all sorts of instruments. The NASA C-130 was there. That's what you were doing. I don't know what else you were doing. We didn't see much of each other because there was a whole lot to do just to make... There was a lot to do, a lot of wine to drink and good food and the like. And NCAR was just a really fantastic place to be for me. Toga Corps was another one. This was, we had to go to Honiara with the Electra aircraft. And we had to be there for 2 months. I took my son out of high school. He was in his senior year and wasn't doing anything useful by then, so I took him along with me, and we learned to dive there, and we did lots of flying out over in the research area to the northwest of Honiara, making measurements with a radar in the back, and I'll talk about that in a minute. So working at NCAR was just amazing because there was all of this Earth measurement technology that we were developing and operating on the aircraft and the radars and the like. And really the last thing I did at NCAR, and this went on for 10 years. If I'd only known when I started, I might have done something else. But we realized that the sort of traditional way of studying severe storms was to put a couple of ground-based Doppler radars out. And when a storm came by, you'd scan up through the storm. Now the problem with that is that if you just think about the probability of having a storm in the sweet spot of observation of 2 radars that are stuck in some particular place on the ground, you realize that's not going to happen very often, and they'll frequently be in the next county or something. And that if we built a radar, a dual Doppler radar, put it on an airplane and flew by the storm, we could make the same measurements. And the way to do that is have one beam looks forward, another looks aft, and scan around really fast. And so we built this thing. And this is just a cut from the BAMS article showing some cross sections through storms and reflectivity and velocity fields. And here's a cut. This is a reflectivity field through a tornadic storm. We can see the low reflectivity core of the tornado and some very different velocities through there and high spectral width from the Doppler system there. And the real fun of this was that we built a radar that did everything we could think of to have it do. One of the problems is a ground-based weather radar scans at about 20 degrees a second. The reason being that you have to look long enough with the radar at any particular spot in order to get a statistically significant and accurate sample at that spot. So you're limited to a certain scan rate. And that's why they scan as fast as they do and don't scan any faster. And so this is the number of independent samples here, and this is about 30 samples. This has to do with the spectral width of the variance of the Doppler, the amount of turbulence in the cloud. And if we scan fast enough to get at high resolution measurements with a airborne radar, we are down here at 1 sample, and we needed 30. And so what we had to figure out to do is we had to send out a complex waveform that the military had been doing for all sorts of military systems, but had not been used for weather. And so you sent out a bunch of different samples in range, and you could do a few other things. And by doing that, you could get as many samples as you needed to get the accuracy, and we could get the same kind of accuracy there. And the interesting thing about this is we had to be really competitive to pull this off. Because to do this, we had to spend about $15 million. And NSF didn't give NCAR any extra money. And so the way we got the money was to use all of NCAR's flexibility for about 3 years. And this really irritated the atmospheric chemistry folks because they were depending on that money, and they also were depending on this airplane, and they were just frantic that we were going to make the airplane weigh an extra 1,000 pounds to do the modifications to hold the radar. And we thought that they were going to ruin their whole future because we would make the airplane weigh a little bit more. Well, we had to fight the battle. It's kind of like, you know, competing in track. You had to be willing to fight and win. And everybody, in the end of the day, discovered they could still do what they were doing. Really, once I got that done, I did some management, and I came here. And you know, it was very exciting there. When I got here, this is my last slide. When I got here, it took me a year to figure out what on earth was going on here. But something I figured out very quickly was I needed to figure out about these space mission things, which I'd not done. And so I talked to Chet Klublinski, and I said, hey, I need to hang my hat on your project and just help, do whatever's needed, just to see what's done in order to compete and win, and make a really exciting space mission go. And so in much of the same kind of way that I did all the Eldora work, I went and repeated a lot of really good work that was going on at JPL. And you know, there were a bunch of lessons there. One of them is that, to my great surprise, we'd figured out all of the science traceability matrix stuff at NCAR when we built Eldora, because that's what we had to do. We had to convince the community that we knew what we were doing. It's the same kind of thing we do here at NASA. I'd also had to learn how to be project manager there, because that was a big project. And you know, somehow, you know, I figured out, and you know, a really good high-performance team helped me figure out and helped us do all the project management stuff, managing the money, having, I don't know how we came up with 30% error budgets for things we didn't understand too well, but we figured that out, and figured out how to have smaller error budgets for other things. Argued that we were going to spend all that money. This contingency was money we were going to spend. We just didn't know how. So somehow this group of about 8 people who built Eldora figured out how to do that. I got here, and it just, you know, this kind of thing just seemed like, well, this makes sense. This is how you do it. And Aquarius was just a great thing to hook into. And it's like Eldora, it's significantly exceeded the designer's dreams. I mean, it's met all of those goals, but it's done better. It's more accurate. You know, the weekly stuff is accurate where we're looking for monthly. It's accurate closer to continents. So it's been a great ride. So that's how I got here. And that's the whole story.
So we'll have a few comments or questions for Peter. You have something?
Piers has to leave.
I'll go.
I could tell by his body language.
So besides this, you talk about radar
Yes.
when you came here, which is something you've always been interested in.
Yes.
And what would you do?
What would I do?
Yeah.
Here?
Yeah.
Now?
Yeah.
Well, I think we're doing a lot of really interesting things with radars. I think that and radiometers. I think that electronically scanned beams. I think that we should build some more aircraft instruments, because that's how you prove the technology before you put it in space. I think the applications to Earth's surface measurements are really obvious, and that I think we're doing a lot of the right things, but I think emphasizing it even a bit more is a good idea. I think not worrying about whether JPL thinks they're going to do it and we shouldn't, forget that. We can work with them.
Good to know.
And we have people who are working on along those lines, and we need to support them, even at the expense of some of the other things we're doing.
Not a nuisance, though. Sorry.
Yes.
Okay.
Excuse me?
What's next?
What's next? You know, there have been a lot of times, quite a few times in my life, when there's going to be something next, and I don't exactly know what it is. You know, think of going off to college. Think of being, deciding for a whole bunch of reasons to go into the Navy. Think of coming here. That's as confusing as anything I've ever done. It still is confusing. I've been in a supervisory position of one sort or another since 1969. So what's next is not doing more of that. I think I've done that. You know, for openers, I think what I'm really interested in, besides moving out of my office and into another one that's small, is playing around with some of the tools that allow us to look at climate data and in forecasts and things like that. And a lot of those tools are really good, but they're also really obtuse. Particularly insofar as there's so many things you can look at. Different measurements of the same variable, confusing lists of variables. And so for the uninitiated, and I'll be relatively uninitiated because I just kind of know about, I've looked at those lists, it's pretty hard to penetrate those things. Go open up Giovanni and decide you're going to do something with it. Well, you can if you're a real expert at some particular field, and that's easier. The less expert you are, the harder it is to penetrate those things. So I'm interested in that problem. And beyond that, I don't really know. That's a good place to be.
Okay, I think this was a great turnout given the weather. So please, let's stand.
Thank you for coming.